A high-pass filter is a spectral effect where the high frequencies of our input signal pass through without being reduced in amplitude, but our low frequencies are filtered out and reduced in amplitude. We can create a high-pass filter by modifying the way that we created a low-pass filter. There we had parallel processing, where one path was of our dry input signal, and then we had a second parallel path where we introduced one sample of delay. For a high-pass filter, we're going to modify this design by adding a multiplication by -1 on the parallel path. This is going to flip that signal upside down. The result of this is we're going to change where we have destructive and constructive interference. For high frequencies, when we add the two parallel paths together, we're now going to have constructive interference. So those signals will pass through. But for low frequencies, we're now introducing destructive interference. When the two parallel paths combine together, we actually cancel the signal out. So let's jump over to Matlab and look at how we can implement a high-pass filter. Here in Matlab, I've started a new script that we can use called high-pass filter. My approach that I'm going to be following is very similar to what I was doing before with the low-pass filter script. In fact, we're just going to make some modifications to our code and look at the result and how it flips from being a low-pass filter to being a high-pass filter. So let's copy over some of these things like working with our impulse response and going through this loop. So I'll put these over here into our high-pass filter. And we'll use X as our input and keep track of the sample number. We'll prepare Y, and then we'll go in through this loop to process the samples of X. Now the difference here, I'll start out with a basic setup, is that we're going to take our dry input signal at the current sample, that's X, and in this case, we're going to have a -1 times the previous sample. So we could do it a couple different ways. We could just subtract off the previous sample. We could do plus, and we could do -1 multiplied by the previous sample. All these things would be equivalent. So let's stick with this because I think that it follows very closely with our block diagram. We have the summation of the two paths, and then also on our parallel path where we have the delayed sample, one from the past, that's when we have our multiplication by a value of -1. So let's go ahead and run this script and print out down below what Y is. That's going to be our impulse response for us to use. So we run this. We can see that our impulse response is similar to what we had before with a very important difference. And now our impulse response is going to be 1 and -1. If you remember from our basic low-pass filter, what we had before was that our dry path and our wet path were identical, either 0.5 and 0.5 or 1 and 1. So in this case, the important difference for a high-pass filter is that the gains are going to be different. One is positive and the other one is negative. So I can come down here. Let's create our impulse response. H is equal to 1 and -1. Now we could analyze that by using the command freq_z of H. So if we run this, we'll pop up a new plot that shows us what the frequency response is of this type of processing. So here we're seeing that we've created a high-pass filter. The low frequencies now are the ones that are being reduced in amplitude, and it's the high frequencies that are allowed to pass through. Again, the way that we've set up with unity gain in both paths, we actually end up combining the signals together, and that's going to cause an increase in 6 decibels over here for high frequencies. If we wanted to, we could use this system with convolution in order to create some output signal Y. We'll do Y convolved X and H. In this case, let's switch our impulse our input signal from being an impulse over to being white noise. So copy this part over from before, bring that into our high pass filter. Script, let's go ahead and stick it down here. So we're definitely just doing the processing, working with H and working with this input signal, X. I'm going to scale the amplitude now to be 0.2. That way it's not too high in amplitude. It's going to fit within the range of 1 to -1. And so what I should be able to do is listen to the result, where we've got our output signal that's been processed by our system, H, and this signal, white noise, and listen to the result. I'll even compare it down below between the X, which is noise, unprocessed, the flat noise, and the high-pass filtered one. So let me clear some things out. Now let's listen to the two things side by side. So here's the original noise, unprocessed. And here's the high-pass filtered version. So in this case, it's definitely an audible effect. We can tell that there is a lot of gain reduction that's been applied to the low frequencies. We're not hearing the low frequencies as much, primarily just the high frequencies. So let's go back through and also make this system unity gain. So just like we saw before, by having 0.5 multiplied by the whole thing, now instead of boosting the high frequencies by 6 dB, we're actually going to just have those go right up to a gain of 0 dB. So now we've got our appropriate frequency response for an audio high-pass filter, where we're not trying to increase the amplitude per se, but what we're actually just trying to do is let those high frequencies pass at 0 dB, and then from there, cut the amplitude of the low frequencies. We could implement this up here in our loop if we were trying to do the processing this way in our own code. Rather than using convolution, we could just add that 0.5 out front. We would accomplish the same thing of having unity gain. So there we've been able to explore now how to modify our code that we had before that implemented a low-pass filter. We've modified it now by adding in this very important -1 here to the delayed version, the delayed signal. And what that does is it flips wherever we had constructive and destructive interference, those frequencies. And now we've been able to implement the high-pass filter.